Hello, good morning, good afternoon, and good evening, and welcome back to another episode of What's New in SimCenter Star System Plus from Engineer to Engineer. I'm Rodolfo Piccioli, and together with me today in the London Hammersmith Studios is David Mann from the Product Management team. Welcome, David.
Hi, Rodolfo.
David, do you want to say something about yourself before we start?
Yes, I'm one of the technical product management team for SimCenter Star CCM Plus, and specifically I look after the area of multi-phase modeling.
And this is a great release for multi-phase, a lot of multi-phase enhancements, opening new applications and so forth. And I think actually, David, you are going to start talking with multi-phase, right?
That's right, Rodolfo. It is a really exciting release for multi-phase, and in this release, we have a number of connected features that enable applications such as e-motor cooling in a way that we haven't been able to do previously. So those features that I'd like to talk about are centered around mixture multi-phase, and specifically mixture multi-phase whilst using it together with large-scale interface modeling. And what they do, they really add mixtures to the hybrid multi-phase modeling that we've been developing for a few years now. And the idea of hybrid multi-phase modeling is really about using the right model locally, so not being limited by the assumptions of any one model like VOF or mixture multi-phase or Lagrangian. They all have a range of applicability. And so in real-world problems today that grow ever more complicated and ever more multi-physics, increasingly those traditional models like VOF are stretched beyond their range of applicability. And so it means that we need something more. And that's where hybrid multi-phase comes in. And what we've done in this release is to add mixtures to that book of multi-phase models that works together. So there's three features that I'd like to talk about. The first is the addition of a new phase interaction model that allows Lagrangian particles, so that could be droplets usually, or bubbles or solid particles, to transition to a subgrid dispersed mixture multi-phase phase. And so you would perhaps use that in the context of a jet breaking down into smaller and smaller scales, for example. That's an application that's traditionally very difficult to do because you have a cascade of scales from a jet down to particles or droplets that may be tens of microns in size. How do you model that with one model? If you do that with VOF, you're talking about multi-phase DNS. It's not practical. If you do it with Lagrangian, you have to assume that your jet initially started as a stream of Lagrangian particles, so it's already broken up. If you do it with mixture multi-phase, it's all kind of dispersed anyway. None of those three models is correct in its own right. And so using them all together provides us the ability to have a set of modeling that works very affordably and efficiently to give accurate results. So now we have this ability for Lagrangian to transition to mixture multi-phase. So you can imagine that we have a resolved jet using large-scale interface modeling. It breaks up into droplets. Those droplets are transitioned to Lagrangian droplets. They're ballistic in nature. They don't go in the same direction as a gas. So Lagrangian's the right model there. But they keep breaking down. Maybe we've got the secondary breakup models on in Lagrangian, and they get smaller and smaller and smaller. Eventually, we've got a huge cloud of Lagrangian droplets. That doesn't make sense. It's expensive. It's not giving us anything. It moves with the background gas. That wants to be a mixture. And so that's where this new feature comes in. It allows us to transition those droplets over to a mixture representation. But we've done a lot of work getting the size of those droplets right. We track their breakup to the smallest scales. We know how big they are. So what do we do with that information? Well, that's the second feature, and that's S-gamma, together with mixture multi-phase and MMP LSI. And that allows us to transition that data that we've got in terms of droplet sizes into that population of droplets. And we adjust that as more and more Lagrangian droplets are coming over. And then we have all the population balance machinery, so we can look at the further breakup and coalescence of those droplets to the very smallest scales. So now we've got this predictive route using hybrid multi-phase modeling very efficiently through those different scales. And then I said there were three features. So the last feature is the ability for Lagrangian droplets to impinge into large bodies of fluid when you're using MMP with large-scale interface modeling. So you can imagine Lagrangian droplets are hitting a free surface. Well, what happens if that's the same substance? So we've got oil hitting oil. We don't want to track Lagrangian oil droplets in oil. That doesn't make sense. So we transition them over with this new feature. So that's 3 new features. And together they, as I said, they enable things like e-motor cooling applications. So if you consider an example, here we have jets of oil coming in. Well, we're resolving those using large-scale interface modeling. So that's a bit like VOF, but just locally. And then those jets, they hit the end windings and they start to break up. And so we have blobs of fluid. We can transition those to Lagrangian with an already existent feature. And so Lagrangian is then the best model for these ballistic droplets that have high momentum. They go in a different direction to the gas, but they keep breaking up. And particularly in such a kinetic environment such as e-motor cooling. And so we get ever smaller droplets, and we can transition those to a mixture with their associated sizes, which is what you ultimately see in that example.
3 terrific enhancements really to mixture multiphase. And if I may, I have an observation that I'm curious to see if you agree with this. But some of these the enhancements, like S-gamma, was already present in oil area multiphase, and now it has been implemented also in mixture multiphase. So several times the problem of multiphase simulations is not the lack of physics in SimCentral StarSim Plus, but the computational time it takes to run and to simulate these applications. And I think that implementing some models that were previously in oil area multiphase, also in mixture multiphase, will actually enable many more applications that were in theory possible in oil area multiphase, but the computational time would have been too long for the computational power that a lot of customers have.
I totally agree, Rodolfo, and that's really what these features are about, and hybrid multiphase as a whole. It's about affordable accuracy. It's about making applications possible or making them cheaper. It depends on which angle you come at it from. And really it's about, if you consider a kind of Pareto front of cost versus accuracy, it's about moving that. It's about moving the whole thing. So you can cash in these new features either as more accuracy or in terms of reduced runtimes. It works either way.
Good. And for the next enhancement, we stay still within the multiphase domain, but to a completely different model.
That's right, Rodolfo. So you may remember in the last release, we introduced something very exciting into our multiphase world of models, namely the SPH solver, or smooth particle hydrodynamics. So in the last release, we introduced that for powertrain type applications. And you had the ability to solve the flow of oil over gears, that kind of thing. But you had to initialize in a certain depth of fluid to start with. One thing we were missing was an inlet, and that's what we've added in SimCenter StarCCM Plus 2406. So we now have an inlet boundary condition for SPH, and that can be a velocity inlet or it can be a mass flow inlet. And so that opens up a larger range of applications. So within powertrain, that opens up cases where we have specific inlets with jets of oil coming in onto the gears, for example, or other areas like vehicle water runoff, where we're interested about how water flows on the surface of a car. So we might be interested, are we getting water going into the HVAC system, for example, or is there water getting in through a side window? Or perhaps water's getting into the trunk of a car and going all over our laptop. Those kind of simulations become possible with an inlet. So a really exciting addition to our SPH capability.
Exactly, yes. And now David, stay with me here, but for the next set of features, we're moving to a colleague, Cedric, who's not in this office but working remotely. I think he's already... Yes, I can see him. Hello, Cedric.
Hello, Rodolfo. Hello, David. Nice to virtually see you, or nice to see you.
Our pleasure here. Thank you very much, Cedric.
You're welcome.
So today you are going to talk to us about a couple of very interesting features. And do you want to say something about yourself first?
Yes, sure. So I'm Cedric Tachot. Some of you already know me, some of you not. According to my accent, you will easily guess where I come from. And I'm working in the platform product management team as a technical product manager for design exploration.
Good, good, good. And actually, the first feature you are talking to us about is about design exploration. Please go ahead.
Yeah, sure. I'm really excited to introduce a new feature we worked on, which is basically reusing a previous result. So the idea behind Scene is to leverage the computation you already did to initialize the next one. So how it works, it's really simple. We look at the parameter space and we have a distance criteria. So with this distance criteria, we find the closest available design in the design space. We take back the result and we use it as an initialization for the next design. Doing so, it allows us to converge faster to the solution. So the main intent of this feature is to go faster to a result by reusing something you already computed. It appears to be really efficient and you have the full flexibility to set which distance you want to set and use design sets to do your post-processing. So like that, you know if the design you computed was reusing another or not. I hope it's clear. Do you understand what I mean, David? Rodolfo?
I think I do, but I have a question. Is it limited to a certain number of parameters, or can you use as many parameters as you like?
Excellent question. Actually, yes, you can use as many parameters as you want because it's only a distance criteria. So it's not limited in terms of the number of parameters you have in your set. Perfect question. And the short answer is yes.
Good, good, good. Another question. I assume that the time we save thanks to this feature is extremely case dependent, but do you know more or less the order of magnitude based on the tests that we run internally?
Yeah, so actually we did a small test case in 2D where we observed, it was our first test, we observed 36% reduction time in the total turnaround time of the study. And we had some industrial evidences showing for a customer in an optimization study, because it works no matter what is the study type, that he was obtaining roughly 50% faster turnaround time using this feature. So in some cases, it works less good because you have high nonlinearities in your response space. But in what we observed, in most of the case, we observed significant gains. Do I answer your question? Yeah.
It answers. When you were mentioning high nonlinearity, probably you mean that the closest initial conditions is not necessarily the closest to the final solution.
Exactly. You can easily imagine such cases for transonic airfoils or things like that where you have nonlinearities. It's typically the case you mentioned.
Sounds like a very interesting feature, and please, all the users watching from home, tell us what you gain with this when using this option in Design Manager. And Cedric, thanks a lot, but you have another feature before leaving us.
Yeah, I will speak on behalf of my colleague Nabila, that you previously met, of course. We are going to talk a little bit about nested simulation operations. So basically, I guess most of you already use simulation operation. If not, that's not good, but feel free to use them. One feedback we had is the fact that it was sometimes difficult to organize simulation operations. So basically, often what we want to do is to reuse some kind of blocks of simulation operations. So you can easily imagine that you have some blocks that could be reused in another workflow. So with that, you can create those blocks and call them from another simulation operation, meaning that from a simulation operation, you can call what we could envision as a subroutine where you call your basic function. So it will allow you to organize way better your blocks and to reuse them when needed. So like that, you have only one block, and if you need to modify it, you modify it only once. So it gives you more flexibility and more organizations in your simulation operation. Does it make sense to you, Rodolfo, David?
It makes a lot of sense, and I strongly believe that our clients will surprise us with their creativity when using this feature. I can just mention what a colleague of us did already using this enhancement, which is having only one template file, which can be used for two different workflows, specifically steady and unsteady, and basically using the nested simulation operations. It is very, very quick to switch between one and the other, as you were saying.
Yeah, sure. So that's a typical use case. So having a template simulation file and calling back several blocks makes perfect sense. And that's typically the use case we had in mind when we developed that feature. So taking into account first steady state to switch later on in unsteady with a single click. So this new feature allows you to do that easily. You're right.
Excellent, Cedric. You presented two great enhancements in SimCenter Star System Plus today, and I really hope to have you here in the London Hammersmith studio soon. And thank you very much, and have a great day.
Thanks to you. Bye-bye.
David, back to you.
Thank you, Rodolfo. Yes, so the next feature I'd like to talk about is not really a multi-phase feature, but it's a feature that's very close to my heart as a user of this feature in the multi-phase world, and it's actually an adaptive mesh refinement feature. And of course, in multi-phase, we make heavy use of adaptive mesh refinements. I'm going to talk about it, and yeah, I'm very excited about this feature. And that is the ability to refine in the Prism layer anisotropically. So, as I'm sure you'll all be aware if you've used AMR, currently if you're refining in the Prism layer, you have to do that in an isotropic way. So if you refine in one direction, you refine in the other directions in the same way. And that can mean you get very large cell counts because you get very, very small cells because your cells are already quite small in the Prism layer, at least in the normal direction. And so what we've added now is the ability to refine anisotropically not only in the direction normal to the surface, so to add more layers to the boundary layer, which you might want to do if you want more refinement. Imagine, for example, your Y+ isn't as you would like it to be. You need more refinement of that boundary layer. You might use it that way, but we can also refine in the tangential direction only, and that's really useful for things like shock waves hitting a boundary layer, or maybe there's a free surface back into my multi-phase domain. Maybe there's a free surface coming into contact with the boundary, and we can refine in that tangential way to just capture that free surface without having refinement in the other directions. And of course, in a 3D problem, that can make a real difference to cell counts and associated runtime. So it's a real benefit in terms of getting our runs to simulate much faster whilst capturing that detail that we care about.
Right, so you mentioned we can refine normally or tangentially or isotropically. What if I have different requirements on different boundaries? Do I have to stick to a general parameter or general criterion, or can I customize it?
Yes, so you can do that. So there is the ability to specify whether you want to refine isotropically, tangentially, or normally on each boundary. You can do that if you want, and break out those boundaries and specify on a kind of criteria basis which boundary you want to treat in which way. And you may want to do that in a lot of applications.
Good. Thank you, David. And for the next set of features, you stay with us, with me today, but we are moving to our colleague Daniele. Hello, Daniele. How are you today?
Hello, Rodolfo. Hello, David. I'm very good, and many thanks for having me here. It's always a pleasure.
It is absolutely our pleasure to have you here. And today you are going to talk to us about three terrific enhancements in SimCenter Star System Plus 2406.
That is correct. I will give you an overview on three new features that are going to be released soon. So let's start, right? So the first one that I would like to talk to you about is a feature which is coming from the integrated meshing development team, and is a new type of sliding mesh interface. So this is a feature which is relevant for workflows for unsteady simulation with rigid body motion, which typically need a sliding mesh interface. This is a new typology of intersector, which is named the metrics-based intersector, which comes with a better scalability and a faster turnaround time compared to the two already available intersectors in SimCenter StarCTM Plus, which are the geometry and the topology-based intersectors. So this is a third one, which is now going to be available in the software, which, as I said, it's faster, it's more scalable, and it's also coming with a lower footprint in terms of memory. So it's just performing better, and it is going to have a great impact on all these workflows that I just mentioned. So unsteady simulation with rigid body motion.
Can you tell us some applications that you think will benefit from this enhancement?
Yeah, of course. So typically applications are unsteady aerodynamic simulation for vehicles where you also want to have the rotating rims, or for example, a mixing vessel in the chemical process engineering industry, or gas turbine in an unsteady mode where of course you have rotation. So the range of application is really broad, and that's why this is going to have a big impact.
Good. And you said you have other two enhancements to present today.
That is correct. I have other two features which are coming from the teams I typically work with. And the first one that I want to talk to you about is a new feature in the adjoint functionalities, which is the possibility of computing adjoint sensitivities for global parameters used in 3D CAD. So this is really an extension of a new functionality that we added in the release 2306, which allows user to compute sensitivities of global parameters. Now we also support these parameters to be used in the 3D CAD, and therefore you can really easily compute the sensitivities and the gradients of your CAD parameters, of the cost functions with respect to the CAD parameters, and therefore really quickly and efficiently understand the impact of these parameters on your design and your flow problems. So again, it's an efficient way, since it is adjoint based, to compute these sensitivities. Of course, then you can also report these sensitivities with a dedicated expression operator that we already added last year. And therefore, yeah, it's a great functionality to really efficiently evaluate the impact of CAD parameters on a specific objective. The third feature that I want to talk to you about is related to turbulence modeling, and it is the support for turbulence model selection and deselection in stages. Now, you may know, Rodolfo, that stages is a functionality that we introduced last year in release 2310, supporting the switch between steady to unsteady type of simulation. Now we are adding a support for selection and deselection of turbulence modeling. Examples of these workflows are simulation where you would have a runs simulation and then switch to a scale resolving simulation. This type of workflows can now be fully automated through the usage of stages and simulation operation without the need of JavaScript, and also with only one continuum. So it is now very easily automated compared to previous versions.
Right. So you already mentioned the workflow of initializing a LES or DS simulation using, for example, a steady runs. And this is possible because all the turbulence models currently implemented in SimCenter StarCTM Plus are compatible with, can be selected and deselected in stages. Is there any other workflow that you have in mind which could benefit from this enhancement?
Yes, there are also other workflows which can be unlocked with stages. And this is because in addition to the turbulence model selection, also the viscous regimes are supported. So basically you could have an automated workflow where you switch from inviscid to turbulent, which is a typical thing that is done to initialize supersonic and hypersonics aerospace flows, so high speed flows. And this can also be now fully automated with stages. So again, also in this case, the range of application is very broad.
Thank you very much, Daniele, for being here today with us. You presented the 3 terrific enhancements in SimCenter StarSim Plus 2406, and I really look forward to seeing you again soon.
Yes, same here. It's always a pleasure to join you for this webinar. And yeah, greetings to you and David in the studio. See you soon.
Okay, David, back to you. Very interesting features from Daniele.
Thank you, Rodolfo. Yes, and back to a multi-phase topic, this time the discrete element method, or DEM. And so we've added some nice new functionality in this release to enable you to model the way particles can stick together to form something larger. And specifically, this is the particle agglomeration model. You may remember in previous versions of the software, we had this idea of particle clumps and the parallel bonds model that would enable you to have particles that were bigger than just a single particle. You could have an object that was constructed of multiple spheres, as it were. What this feature is about building beyond that. So often we have applications where particles could stick together. Maybe they stick together because you're coating them with something, so there's some interaction with a liquid. Perhaps that sticking together is a function of time, so the liquid that you've got sticking particles together could cure, for example, and that could become a more of a permanent solid. Or maybe we're looking at the breakup of particles, where through some interaction and the forces on particles, they may break up and leave you with smaller particles. So we've added the particle agglomeration model to basically give you a framework to cover all of this physics, so we can control as users the bonds that are holding together the individual spheres of our larger clump of particles. So a very nice application that covers a very nice capability that covers a large range of applications, not least things like additive manufacturing, where you might want to kind of melt particles, have them stick together and make a larger whole.
My feeling is that when these features, this is one of the features that customers will surprise us with their creativity using this.
Yeah. And as I say, it's a framework, so it's very much there to build on and set your own modeling and criteria.
And I look forward to seeing what you are going to use it for. And right, so next, David, stop with multi-phase for now, and we are talking about FSI.
We are, indeed, and the difficult problem of contact. So we have already, for our solid stress capability, the ability to model objects in contact, but modeling contact is quite a difficult thing to do, whether that be in DEM or solid stress. And why is it difficult? It's difficult because it's such a short timescale event. So if two things come into contact, one instant they're not in contact, the next instant they are. And that can be numerically difficult to simulate, a so-called stiff problem, because it happens in such a short timescale. And that can manifest itself as something that's difficult to converge. And so in the previous release of the software, we used this methodology for FSI problems called the penalty method, where we would typically allow objects to pass slightly through each other for pragmatic reasons, because that makes the problem less stiff. And so things would go slightly beyond being in contact, but that would get the kind of essence of that interaction between two bodies, and you could then get the subsequent deformation and so on. What we've introduced in this release is the augmented Lagrangian multiplier, together with the a Zawa method, which is a new way of modeling that contact, which allows you to model that contact much more accurately. So you don't need to have this kind of overlap. You can model the contact precisely. It's able to do that because it's a method that's iterative. So we can do that without suffering convergence problems that you might do with other methods.
Yes, and it should be said also that the augmented Lagrangian multiplier method is an iterative method. So, despite being more stable and more accurate than the standard penalty method, can be also slower than that.
It's more computationally expensive, yeah.
Yes.
But then you've got that very precise contact.
I really like the example at home I can see in the video now. So this is a peristaltic pump. It is a type of pump which is normally used in the pharmaceutical industry, in the medical applications, and it can be seen at every rotation the small cylinders in the rotor engage and disengage in a contact with the pipe, and basically using a soft modeling of the contact between the tube and the rollers would probably result in a lack of accuracy, in a non-accurate enough simulation.
That's true, and that the fluid there could be blood, for example, or a biomedical fluid where the stress on that fluid is really important because you can damage the blood cells, and so that accuracy is really important.
Okay, David, thank you. And you have one last feature to present now.
I do. So I started today talking about e-motor cooling with those lovely new features in mixture multiphase. Well, there's two real hot topics in the design of electric vehicles, it's fair to say. One is the design and cooling of the motor. The other is the battery, of course. The battery is the other challenging part of electrical vehicles. And in addition to issues like the overheating and thermal runaway, one of the hot topics is aging. How do I know how long my battery is going to last? Is it going to last enough to make my product a worthwhile purchase for people? And we all know from owning smartphones and laptops, batteries don't last forever, and it's usually the limiting feature for the products that have a battery in them. And so in this release of the software for the 3D cell design, we've introduced two new mechanisms for modeling the aging of batteries. Specifically, we have the solid electrolyte interface film growth model, or SEI as it's known in the industry, and the lithium plating film growth model. And so these are modeling processes which degrade a battery. So as byproducts and the reactions within a battery, we get a buildup of unwanted substances. So in one case, we get lithium plating happening, a kind of electroplating process, as it were, of lithium, which we don't want. And in another case, we get a buildup of this solid electrolyte on the interface area for that film growth. And both of those prevent the battery from working quite so effectively as it did when it was new. So they reduce that life of the battery. And so now we have models to model those mechanisms. You can simulate that aging process within a 3D model to see where in your battery is that life being limited, and where perhaps can you change your design. So that brings us to the end of the last feature. But before we go, I'd like to ask you, Rodolfo, which is your favorite feature in the 2406 release?
Right. So to be honest, there are so many features I love, and all the features you introduced at the beginning about MMP, LSI, and so on, I think they're really amazing, and they will enable so many new applications. But I want to talk about something completely different now that I love, and I'm sure that all our clients will love, and it is the ability of splitting derived parts into subsets on demand. Very, very long name for a feature, so let's see an example. In this case, we see a plane section, and this plane section is cutting through plenty of parts. So it will be quite difficult, for example, to see the maximum temperature in each part that this plane section is cutting through. And so now in SimCenter StarSystem Plus 2406, we have a new option, which is split the derived part. When you do this, several new derived parts will be created, each of them with the same properties of the parent derived part. So if the parent is a plane section, also all the new ones will be plane sections. But each of them will cut through only one, for example, one volume, and it will be much easier to do further post-processing, like reports and so on, or plotting them in a scene. And the parent part is still available, which can be used for further post-processing, or again for splitting into other parts. So very, very tiny feature, but I'm pretty sure that a lot of users will use it and love it.
That's a really good usability feature, I think, that will save a lot of time.
So I said that this was the last feature you presented, David, but now we reached the moment that I mainly love in this show. Are you ready?
I'm ready.
Yes, let's give just 1 second to our technical team to bring the laptop, and then back to the 3 minutes challenge. Okay, and here we are. So for those of you who are not familiar with the concept, David now will try to show as many new enhancements as possible in just under 3 minutes. David, you said you're ready, your laptop is here.
Ready?
Have you practiced your fingers?
Yes.
Okay, so 3, 2, 1, go!
Okay, first feature. Simulation guide. We had it before. Now you can print the simulation guide either to PDF or paper. Now a geometry feature, 3D CAD. What we can do now, if I import a CAD model to demonstrate this on, is to explode the view. So we can see this drill bit now. I can scale to explode in different dimensions. Then next, staying with 3D CAD, I can look at multiple instances of the same component in 3D CAD, and I can defeature them just in one place, and all the instances will similarly be defeatured. Then the next one is to select multiple faces with painting. So I can drag the mouse across and select lots of faces in 3D CAD. Now, next thing I'd like to show you is to create a bounding.
And 1 minute has gone.
So now we have a geometry. I want to select a bounding box, which I can do by part surface. So bounded shape per part surface, that feature. Right. Next, I can extrude.
I think that's what you're doing here.
I can make this a parameter.
Yes.
So I have a meshing parameter selection and control.
And in this new version, you can also customize with the parameter the number of layers in the extruder and many more things. Sorry, I shouldn't interrupt.
Yeah, so now what I'm doing is using a local coordinate system for clip planes. So I can do that here and select that local coordinate system. So I'm going to move on to a new simulation now to demonstrate some of the next few features. You like this one? You like this one? So by plane section, I want to split
1
this.
minute left.
I want to split this by part, which is your favorite feature, I believe.
Yes, sir.
So we can do that, and now we have split by part. We have two parts. Next, I want to customize my residuals, or any plot for that matter, and I can now set the color of my choice interactively. There's a new type of report, which is a monitor derivative report, which I'm setting up here so we can monitor derivatives, which is rather nice. And then finally, I'm going to introduce a new functionality by stages. So I'm going to select different turbulence models at different stages in the simulation. So we go for laminar, and then turbulent in our 2, 3 stages.
2, 1. Done. And I think.
How many was that?
You are 11, I think. As usual, I may be wrong. All the users attending from home will have the infographics on the screen. And, I think it's 11, which is a very, very good number. So, and you managed to do this without touching any of the multi-phase feature that I love. So great. And we are now at the end of this video about what's new in SimCentral Star System Plus 2406. As usual, there are a lot of people that I would like to thank. I do this all the time, but it really comes from the deep of my heart. So let me say a big thanks to all the development team and the product management team, represented here by David, but there are many more people than David. And without the development team and the product management team, it's useless to say that all these enhancements that we have seen today wouldn't exist. What else? What you have seen today is just a very, very tiny part of all the enhancements implemented in SimCentral Star System Plus 2406. It is always difficult to do a selection when there are so many great features. So for example, the journey into the GPU is still continuing. Liam McManus, Mr. GPU, is not here with us today, but we are not stopping developing that part. In SimCentral Star System Plus 2406, we have, for example, the grid sequencing initialization, the surface-to-surface radiation, the segregated fluid isothermal, the partial sleep, and what else? The right part, the monitoring. So many new enhancements that we didn't have time to talk about in detail. And I think we are at the end really of this video. David, thank you very much for being here. It has been an honor to have you here in the London Hammersmith studios today.
Thank you, Rodolfo.
And see you soon at the next episode of What's New in SimCentral Star System Plus, from engineer to engineer.